Starting up, my favorite shirt is the one I just actually bought for my son. It says "Danger Pinata" and it shows a hornet's nest, which I think Danger Pinata hornet. Okay, Zoom. One needs to adjust one's sense of humor for Zoom, perhaps. Just like my glasses don't allow me to see. Okay, now I can see you. Um, Everyone has the Zoom backgrounds, right? That show what their idealized life is like. It's like Facebook, but for Zoom. When you put on a show, this is my actual bookcase in my house. If you want to inspect my books, you're welcome to do that. I can't zoom in on it, but you can see the way I organize the books, not by color, not by size, not by subject, by how recently I decided to put it on the shelf and where there was space. Okay. So that's my life. We have basically 2, 3, in my mind, class sessions before the final exam. And so just to sort of talk about administrative things, and I think I've got the recording going. Good. So should be in the recording. Today, chapter 11, if things go the way I would hope that they would, but if they don't, because y'all want to ask me bunches of questions about the last batch of material, that's fine too. We could go there. But this week, at least, at some point in time, we'll be talking about the material in chapter 11. That may drift into next week as well. Probably not. And then we're either going to be talking about random effects models, okay, or logistic regression this coming Tuesday. Both are fine by me. Both are worthwhile. Both are the sorts of things that would be a next step, if you will. So, if any of you are working away on your thesis work or whatever, and you're going to need to use or study random effects models, let me know and we'll sort of lean that direction. If, on the other hand, you're going to be dealing with a situation where your response variable is categorical in nature, again, an email or something like that will allow me to sort of plan for next Tuesday to be tackling the question that the most of you would want me to consider. Thursday of week 10, next week, Thursday, 9 days from now, we should be going over questions from the sample final exam. And like Daniel asked me last week, and I want to just remind you all of it this week, by later this week, I should have all of the exams graded, and I should be able to let you know approximately where you stand point-wise, okay? And I'm going to talk to the grader again. I'm not that much more hopeful than last time, but, it's worth a try. And I did have an experience last quarter with one of the graders that I had. That grader literally came in right after finals were over and graded everything. I thought, earlier would have been nicer, but I was appreciative at the time that it was better than no work done. So I'm still going to be offering that grader the option of continuing to sort of work on grading. But right now I'm leaning towards a did you do it or not sort of grading scale. Okay, the answers are online, and if a student did it, I think full credit would be appropriate at this stage. And so leaning that direction and just to get the grader to get some scores done. So by Friday of this week, I should have available to all of you via email a little file. Excel is the form that I'll use. Hopefully you can all use Excel somewhere on one of the machines you have access to. And you could enter in your midterm score, your other midterm score, what percent of the points you've done for the labs, for the homework, etc. And for most people, that's full credit for all the labs because if you did them, you got credit for doing that. And it'll let you know where your grade is currently. And furthermore, it will let you know sort of a third of a letter grade higher what score you'd need on the final percentage-wise to be able to achieve that. And similarly, A third of a letter grade lower, what percentage score, if you were unable to achieve it, would cause you to have a slightly lower grade than current. That information, along with information about, and this is all built into the spreadsheet, that information, along with information about how the grading schemes will impact that, because according to gradings option 1 or 2, the cumulative final versus the one that emphasizes just the more recent material, you'll be able to say, oh, look, it's going to be a little bit easier for me to maintain an A minus if I take option 1. But if I want to increase my chance of getting an A, maybe option 2 would be better. I mean, I don't know what the situation is. It all depends on the numbers, and the file will inform you of that. And then you'll have about a week to think about it. Also, during week 10, I will be identifying 3 different time slots during the week. One of them will correspond to the official finals time slot for this class, where I will be literally sitting in a Zoom room. And if you sign up to take the test during that time period, which is your choice, you don't have to, I'll put you in a Zoom breakout room by yourself, and you'll be working away on the test. But if you have the desire to ask me a question, Steve, could you please rephrase this? I would be happily able to do that. Usually I go in order of when I see the hands going up, and usually everyone is happy with that as an option. You don't have to, but if you are free during a certain time slot, and I'll give you 3 of them, you sign up for it and let me know that that's your preference. I'm also going to be offering students in my other class, the Stat 218 class, 2 sections of that, the same deal. And so when you do log in, you might very well see a whole bunch of people that you've never seen before, and that's okay. You'll all just go off to your breakout rooms and work away on the test. But again, that's your choice. Okay, so that's a lot of sort of administrative organizational things. Do any of you want to ask about administrative or organizational things to clarify? Or was actually what I said clear? Because sometimes that's a problem. I get 1 thumb up. Not even 2 thumbs up from Denise. Okay, if I'm stretching across other people, somehow 3 thumbs have occurred. Okay, so if you do have administrative questions, you can always bring them up on Thursday, okay? And that's fine. How about subject matter questions? And again, I'm very happy at this stage if you want to stop and pause and talk about characteristics of, say, fitting a polynomial instead of a categorical variant of a quantitative factor. We could go over that or any of the other things that could be viewed as before chapter 11. Now's a really good time. I'm not trying to hint at you, but now is a really opportune time to sort of ask that one question that you thought of a week ago but forgot to ask a week ago.
How do you do standardized residuals in JMP?
Okay, when you save the residuals, there is the option of saving the residuals or saving standardized or studentized residuals.
So
it's one of the. Go ahead.
Sorry. So studentized is the same thing?
Well, depends on the book. Okay, so let's talk about what it means to standardize or studentize a residual. Okay? If you were to take, and I don't really care for this class a whole lot. Just saving the residual should be sufficient. But we do have the notion in the context of a regression, if you have an unusually high leverage point because it's far away from the average X, the trend line tends to go closer to those data points than to data points in the middle of the X range of plausible values. Just due to the laws of mathematics, that's just what happens. And so some books will say, aha, let's take our residuals and divide through by the standard error of the regression line, if you will, S sub e, or the square root of RMSE. And I would call that standardized. Mm-hmm. But another approach is to divide through by the standard error for a particular data point based on knowledge of the X values corresponding to that. So literally, the high leverage data points will tend to have smaller standard deviations. They tend to be closer. So let's divide through by that variant of RMSE. It's RMSE times the square root of 1 minus H sub II from the hat matrix. If you basically take the leverage, yeah, and incorporate that into your understanding, I would call that studentized. The studentized residuals should have mean 0, standard deviation 1. Standardized, same concept, except done a little less precisely. And I have seen one textbook that's very well known in statistics swap the names of those two terms. So I always do a quick test calculation if it matters. In most cases, it just doesn't matter a lot. But in most cases, if I'm going to bother with it, I will choose what's called studentized over standardized. That's more likely going to be providing you something that is going to lead you the right direction. Does that answer your question, Daniel?
Yes, it did. I only really asked because on last homework, it was asked to make a plot with that, but I couldn't find the option. Only studentized, so.
Yeah, studentized is better. But
Okay.
if you literally took the regular old residuals and divided through by the RMSE, root mean square error, that would be standardized according to our textbooks. The white textbook that's most often used in stat 513, I'm sorry, not 513, 523 and 524 it's going to swap those two names, which causes a lot of confusion for people. In the same way that the term general linear model in this class means one thing, but in the context of 524, it means something else entirely. Sorry, dudes. Okay, so that answers or partially answers one question. Usually on a final exam, I'm not going to sort of really fuss over that issue. When I present residuals, it's for you to assess normality, equality of spread, and curvature in a plot of the residuals against one of the x's or perhaps against the fitted values, looking for problems, if you will. Someone else? It does seem like it's that kind of a term. Has this year seemed long to you since like last spring term? I mean, I know a couple people who are just totally happy to be at home all the time. Or when they do go out, which is rarely, they happily wear masks. I don't understand that, but um, I am thinking to myself, oh my gosh, regular winter terms are somewhat a challenge just because the weather and other things, but this winter term has been challenging. And if this class has been challenging for you, I'd love to say great, because that means you're learning. But to be honest, in this new format, it makes it harder for me to feel confident that those challenges are always good. So hopefully you're learning something that will benefit you along the lines as you proceed through your career. And I'm not digging for compliments here, but I am admitting essentially that this is not what anyone signed up for in life, but we get to deal with it. And that is itself, well, it's a lesson for life. I'll be better able next year to deal with unusual circumstances where students need extra grace. because I think a lot of people this year have needed a lot of extra grace just to make it through stuff. And so that's good, I guess. Last call for questions on anything.
Yeah, I
Um,
got one
Oh, sure. Yeah.
so it was on the last homework, and
Yep.
it's kind of a simple, like, just JMP question, and it was when I was looking at the plot of the residuals against the fitted values.
Sure.
What's the easiest way to produce?
Well, it's not to mute your microphone, Harrison.
Oh,
What's
sorry.
the easiest way to produce? And then you hit mute.
Easiest way to produce the summary statistics.
Which summary
So it
statistics
was
do you
about the
want?
treatments. So it was like for each treatment, it wanted just the mean and the standard deviation, I believe.
Okay. So yeah, if I have saved residuals and if I have a categorical explanatory variable, I just use fit y by x. Because that will give me, when I say means and standard deviations, it will show me the means and the standard deviations for each of those variables. For each level of that categorical explanatory variable, I'll have the mean of the residuals, and that should be 0, we would want, and the standard deviation should be about the same. But you can also, with fit y by x, do the test for equal variances, which is a way of looking for equality of spread. Does that get to your point,
Perfect.
Anderson?
Thanks.
Okay.
Yeah.
And Martika, I think you had a question also.
Yeah, I was just wondering, I have had a lot of difficulty with the conceptual questions at the beginning of both midterms, and I was wondering if you
Yeah.
had any general guidance on how to better prepare for questions like that on the final.
Okay, so this is often something which is a question that's asked even in a regular term, but I think it's more so this term, not this term, but this academic year with using Canvas. Okay, so let me explain the purpose of conceptual questions on a test in the first place, and then we'll head towards the challenging thing with them, and in particular with Canvas as the tool. Conceptual questions, they're not really because I want to check to see, can you do the basics, the things you just learned? They're rather, do you understand the concepts behind the techniques that we're utilizing? I could easily write a test that every single one of you could get an A on. Now, some of you are thinking, well, that would be a winner. Well, yeah, but that's sort of like the algebra test that you all got something like 95 to 99% on when you were in middle school or early in high school. And the reason is you can always, if someone tells you exactly what the questions will be, you know exactly how to answer those questions. Okay, so I love to bring up questions that check your understanding at a different level or in a different way. So one classic example of that is the question about hypothetically, if you were to find X being the year that a student was admitted to Cal Poly and Y is the year that they graduated, for people who are admitted as first-time freshmen, is there going to be a relationship? And if so, what would the slope be? What would the intercept be, etc.? With a bit of thinking, you could say, well, supposing X were to go up by 1 year, what happens to Y? That's exactly what the slope is. But that itself takes a little bit of a jump for many students to sort of remember, hey, here is the interpretation of the slope. And then when you say, well, what does it mean for a 1 unit increase in X? That means, okay, I have to think this through carefully. A student was admitted at age 19 instead of 18. They started at age 19 rather than an 18-year-old. They put off college by a year. Well, if you put off college by a year, you're going to graduate being a year older than most of the entering classmates that came in right out of high school. Okay, so this is the sort of thinking that the really solid student is going to sort of have in mind, but it's a question that they've likely never seen before. So how can you prepare for that? Oh no, I forgot the one thing about the Canvas thing. Usually that's going to be an open-ended question. If I had you all just write down your answers on a piece of paper, I don't tend to ask a lot of true, false, or multiple guess questions. If it is true, false, it's usually true, false, and explain why. But with Canvas, it takes so much longer. Now, this could be just me, but it takes about twice as long for me to grade a stack of papers as it would if it were in a regular context. So one whole stack of Stat 513 exams all the way through, including every single question being open-ended, I can usually get that done in about half the time is me grading about half to a third of the questions by hand and the rest of them being auto-graded. If I had to do all of them by hand, it would take that much longer. And so I wanted to rely on the auto-grade feature, which makes it harder for me to write the question, giving you the appropriate choices of answers, and then for you all to sort of bubble it in feeling confident. But I think one thing that would be great to do to prep for the final exam is to look over the past exams, especially if you're going to take the cumulative version of the final, and say, do I understand the answers? And could I now explain them now that I've seen those conceptual questions being answered? Second, get together with a friend or four, somewhere in the range 2 to 5 people is a good size group to work with, and go through the process of trying to identify what are some of the key concepts that aren't going to be just redoing lab type questions. What are the key concepts that we could be asked about, and come up with 2 or 3 questions you think are appropriate and write up what you think the right answer is. Pass it to your buddy on the right. Well, if you're not meeting in person, well, on the right in a Zoom room, and each of your study buddies will be doing the same sort of thing. And you could then even discuss. Now, my proposed answer to my proposed question was this. Do any of you want to agree or disagree with my answer? Conceptual question. Do we have the concept understood as a group? And then, hey, how could I rewrite this question to make it even better as a way of differentiating between students who have a solid understanding of the concepts and those that maybe don't have as solid an understanding of the concepts? The point is never to trick a student. The point is to assess whether the student understands the concepts that we learned in one context in a slightly different in a slightly different context, I should say. I mean, we learn an example today. We'll be talking about in the lab the SAT scores in 1982, and you're going to learn about the SAT scores in public school funding and those sort of issues. But I think the real underlying question is, how could I take a collection of possible explanatory variables and determine which ones I should use versus which ones I shouldn't use in my ultimate analysis of the data? So, Martika, this is already a long enough answer, but I think the other thing is find 1 or 2 other students and then talk through those past answers, and then ask in office hours about possible questions that come to your mind relating to more recent material. So that's just a couple of things at first, and then talking to me via email and in office hours is another good thing, because I'm just giving general answers to a whole class. For any individual student, my answer may be a little bit different based on the exact sorts of things they say have been challenging for them. So hopefully that was a little helpful. If you want to rephrase the question, I could attempt to revise an answer.
Yeah, that was great. I'll definitely try to do all of that. Thank you.
I love it. When people say the word great now in Zoom time, I think, yeah, that was great. And I know that's not what you meant, but I immediately run towards the place where I'm thinking, oh, I'm being criticized. No, it's
No, it was
not.
really helpful. Thank you.
But it is, we are all easily, because of life's challenges these days, uh, l- reacting real differently to stuff. I've seen people fly off the handle in a meeting when they were normally the calmest person ever. It's just bizarre what life these days is doing to us. So, look at my bookcase. Any other questions?
Yeah, I got one more.
Yeah, Harrison.
So could you just kind of go over like the general big idea of how we determine normality and equality of spread?
Okay. In the context of a designed experiment or a regression, what we've done so far, number one, save the residuals. Number two, plot them against each of the x's and plot them against the fitted values, the y hats, if you will. The predicted values is what they're often called as well. That won't show you normality directly or equality of spread perfectly, but if you plot your residuals against the x variables, you might see a slight funnel shape. If you see for some x's a wider spread of the residuals than for other x's, like, instead of the residuals going from only 0 to 2, I mean -2 to +2, if they're going from like -5 to +5, it's definitely a wider range. And if you see a wider range in the residuals, you have a lack of equality of spread. Okay, that's one. Number two is if you have equality of spread, which is not always going to be the case, but if you have equality of spread, then just doing a analyzed distribution, you'll see the histogram right there. And that histogram should show you whether it looks bell curve or skewed. And if it looks skewed, look at the normal quantile plot for a straight line. And if you have a straight line in the normal quantile plot, usually we feel good and stop there. So that's really the big picture. But if you had a lack of equality of spread, and if you have a lack of normality, hopefully, like one of the recent labs had on it, you could say, could I transform my y variable perhaps to get something better? And we'll actually see that in my example for class today. So I'm glad you brought that one. You want to follow up on that, Harrison?
Nope, that was what I was looking for. Thank you.
Okay. Someone else?
Okay, hopefully this is the last question. I have at least. So let's say, so for the assumption of independence, is it typically the case that you should not take multiple measurements on the same subject? Because what
Correct.
I'm thinking about are like longitudinal studies, like studies that are observing people over a long period of time. So if you can't take measurements of those same people, I guess, over the whole period, you just have to increase your sample size, I suppose? Or there are like exceptions to that rule where you can't?
I'll say, interestingly enough, yes. Okay, so there is another full-on class, Stat 523, where in a designed experimental context, we can handle multiple readings of the same individual treatment unit. We're going to measure it several times, perhaps even over time, the exact same thing that was treated, we measure it several times. Typically, when you do several measurements on an individual that you've treated one way, you would want to average all of those responses, or if they are changing over time, the values, say you're measuring the pH in something that you just created, and if the pH is dropping over time, you might start with the initial minus the final pH. And so you're measuring really the pH drop. The pH drop could be a better response variable than the actual pH itself. If you have multiple readings on an individual thing that was treated in a particular way, in Stat 513 land, we summarize by saying, well, take all those measurements and boil it down to just one measurement. In Stat 523, we say, well, there are other things we can do. We'll maybe hint at that next Tuesday if y'all ask me to talk about random effects models. And there's another stat class, Stat 419, which is Bio 542. Sometimes that's a multivariate response data. If you have many separate readings on one individual, maybe you want to take them all together as a collection of responses. You could measure one individual in several different ways. And then ask, is there any impact on the individuals on average across multiple characteristics? We could still tackle those sorts of questions. You're asking a great question. 513 doesn't really satisfactorily answer it completely. We say over summarize for this class. Are you okay with that, Daniel?
Yes, I am, at least for this class. Thanks.
And that is the thing. You know, I always remember back to second grade when my teacher told me, yeah, you can't subtract 3 apples from 2 apples. And I thought, well, physically, yeah, but I know about the number line. And so, yeah, you can just go back into the negatives. And so my teacher sort of oversimplified things for me to be able to learn it. That's what we always feel like on this side of the screen. That's okay. I usually say when we're up at front in front of the chalkboard, but you know what I mean. We're always oversimplifying so students can develop a more in-depth understanding of things. If you present everything in its perfect theoretical optimal fashion, you know, the way that a theoretician would say, oh, yeah, that's right. No students are immediately going to understand it the first time through. Yeah, so we feel badly. Oh, well, you don't care how I feel. So if you want to talk in office hours, that's a really great question for a greater in-depth conversation. Last call? Okay, so looking at the time, 12:43 right now, what I'm proposing we do today is I will walk through some concepts, okay? And we may or we may not get to the lab today, but what I don't want to do is to say, oh yeah, just do the lab on yourself, you know, in your own time later. Depending on how far we progress into chapter 11, and what I'm going to try and do is to be a little bit more thorough up front, and then fine tune some understanding, dot some I's, cross some T's in chapter 11, maybe next time, and then the lab we'll probably be doing next time. So if you're the sort of person who knows the person who will be coming in right at 1 o'clock, because that's what they do, you could warn them in advance that we might not be doing a lab today, but we'll see where we get to. So I'm going to go ahead and share screen, and we'll see where we get to. Boom. Okay. So what I'm looking at is my attempt to summarize where we stand and what we need to yet do. And then I'll sort of pitch to you an analogy, and then we'll move forward in the material, our understanding of the whole of chapter 11. Again, working via an analogy is how I'll approach the bulk of chapter 11, but let's see where we get to now. Okay, so if you have many possible explanatory variables outside the context of a designed experiment, or a design experiment where you measured covariates or other x's which might possibly impact y. If you're more of in a observational study analysis, or maybe even a prospective study, but one where you cannot assign individuals to treatment groups, and this is commonly found in biology, where we're literally going to wander through a stream bed and you're going to be saying, well, let's capture every single fish in a particular species that I can. It will record information about what the stream characteristics were like in any given little region, and then measure the fish characteristics in that region. And we could then attempt to try to say which sorts of fish tend to prefer what sort of regions within the stream. Okay, that's not a design experiment, but it is still a very worthwhile pursuit. So things that we need to remember, and these are things that y'all should feel relatively comfortable with so far. If you've got a quantitative variable, that's going to get you a trend line. Or if you got two of them, we'll get a plane. Three of them, it's a hyperplane of sorts. Categorical variables, well, it's going to just give me multiples of whatever I had with my quantitative variable. Maybe I'll have 3 trend lines for 3 groups. And with the interactions, we might very well have 3 trend lines with 3 different slopes. Okay. We also have the concept of, well, I could fit a polynomial model, a quadratic, a cubic. Fine, no problem. I could call those self-interactions if that made myself happy. But, you know, just think you could even have interactions between 2 quantitative x variables, taking that plane and bending it. Okay, so a lot of possible ways we could deal with the data, but really this 5th bullet point here, adding an additional term, a new x variable, or even an interaction where we formerly didn't have one, we're possibly going to be clarifying the picture. If a collection of p-values go down by adding an x variable, you're saying, oh, look, I see something more clearly now than I used to see it. And we do tend to use adjusted sums of squares for the bulk of our quick first initial understanding. But for some particular questions, you would like to control for some, but not all, of the other x's. In that case, you would, of course, need sequential sums of squares. We've also talked about using residuals and analyzing residuals to see if there was a problem or things were good, or you know, and maybe fixing via transforming an x variable or transforming a y variable, adding an interaction. Residuals will draw your attention to problems. Okay? We have not yet, however, talked about which x's should I use? If I collect data on 30 different things, which x variables could be or should be utilized in my look for a relationship between x and y? And how do I compare between models? I mean, I guess normally we do have a, not normally, that was a joke. We do have a hypothesis test to compare between 2 models, one of which is another one, but now fancified. We could make, you know, add an extra x variable, or perhaps even 2 or 3 extra x variables, and we can compare directly. But how do I compare between models where one isn't really just a subset of the other, with maybe a collection of terms zeroed out? Like imagine a regression equation with 6 x's. If I cross out 3 of the betas, require 3 of the betas to be 0, you could use a model, I guess, a partial f-test to do that. But what if I have the choice of using 4 x variables in one model, or 3 very different x variables, not even any of these 4, but 3 different ones? How do I compare between those 2 possibilities? Now you'd think, oh, higher R squared is the better model, but we've got to have some more well thought out criteria than just which is the best by looking at R squared. So here is a reminder of one of the data sets that we looked at earlier this term. And I think I just put it in the wrong window. I put it in the right window, but it was so darn wide, it compressed and shot over to the other window. Okay, so here we go. And this looks funny. Okay. Here we go. Okay, that I think looks good. I've had this problem with Zoom in the last updated version of Zoom. When I drag something from one thing into the screen that I'm projecting, sometimes it changes the way it looks on my screen, and I'm looking down on my iPad, and also it looks messed up there too. So sorry if that has happened too often. My real goal with this data set is to figure out mortality, and this is age-adjusted mortality in various cities from lung-related illnesses. So this is deaths from lung-related illnesses per 10,000 residents in each of these cities. So like Dallas, Texas in 1972 had 860.1 deaths per 10,000 people from things that were like, emphysema, okay, or any of those other lung sort of diseases, things that might impact you if you smoke, but also just asthma, problems with breathing, okay? And the question really was, do the hydrocarbons or nitrous oxide compounds or sulfur dioxide, do any of those impact the death rate from these lung sort of conditions, okay? And if you're sort of in the chemistry or certain areas of engineering, you sort of think, okay, hydrocarbons, nitrous oxide compounds, those are both produced by burning natural gas or gasoline or diesel, okay, or coal. Sulfur dioxide, you tend to, in the 70s at least, most of the SO2 was from coal. And coal was burned in the Northeast primarily for power generation, but also for heating homes. Literally, some homes have coal furnaces. I lived in a home in Richmond, Virginia for 5 years where the earlier owners had coal, and they literally had coal dumped in their backyard, and they shoveled it down and tossed it in the furnace and burnt it. And that furnace was later retrofit to be an oil furnace. And so, we got heating oil, but at one point in time, people used coal to burn in their individual homes. And so maybe coal burning, or maybe just generic things related to burning of petrochemicals or hydrocarbons, is going to be impacting stuff in the air, causing them to not be able to breathe, and therefore die of breathing related things. Now, when looking at that, someone said, well, older people are more likely to die than younger people. So, of course, if the people over 65, if you have a city with 20% people in that over 65 range versus only 9% in that over 65 range, you'd expect a higher death rate from these lung-related conditions, okay? House, the number of people per household, the average education level, the percent of the housing stock that is up to building code. Current building code corresponds to what we want homes that are newly built to look like, but this is the percent of homes that currently exist in a city that are up to code, the current codes. So in other words, if you were going to rebuild it today the exact same way, 90% of the homes in San Jose were totally good, but in Worcester, Massachusetts, it was only 80%. Okay, density, that's number of people per square mile. You'd think New York City is going to be higher than some other places. The non-white percentage, okay, the white collar percentage, people in the white collar industries, the poverty rate, percent of people who are poor. These are all other things even things like the precipitation and the humidity levels that could impact mortality. Just for fun, let's talk about January temperature. If the January temperature is cold, like Minnesota, people stay indoors. And if they stay indoors, they're going to pass colds or worse, the flu to each other. And if they do that, then those that are older who already have difficulty breathing are more likely to get pneumonia and then die of that. So January temperature makes sense. So someone collected, let's just say, a ton of X variables that could be related to the response. Fair enough? Which ones should I use in my analysis? We have these two competing ideas. Having just the right X's that really do matter is, of course, good. Having too many X's you'd think would not cause a problem, but for each X variable that we add that really is not related to Y, there is the possibility of spurious correlation causing us to think there's a relationship when there really isn't, type 1 error. So we have to sort of be careful in our consideration of which X's to use. So let's go down the path and start defining some things that you would want to know about. R squared, you already know what R squared is. It's the proportion of the variability of Y that could be considered explained by or related to the X variables. Okay? Literally, R squared should go up if you add a new X variable. The only way R squared will not increase is if the slope of that X variable you add in is identically equal to 0. 0.00000 slope will get you no change in R squared. Or if it's categorical, if the estimated treatment effects are all exactly 0. 0.00000. So R squared basically you think goes up. You add an X variable, R squared goes up. So your criterion can't be just choose the largest R squared, because the largest R squared model will be the model with every single explanatory variable in it. You don't want to do that. Alternative approaches, and these are better for sure than R squared, okay? Use the model with the smallest MSE, mean square error, or smallest root mean square error. I like that one okay, because the root mean square error tells me if I were trying to predict inside this data set one of the Y values, how far off would I be? Well, the smallest prediction error on average, smallest root mean square error. Smallest MSE is going to be, in some sense, the best models. If by adding a new variable into my model, I reduce MSE, I'm happy. We'll tend to choose a model that's about the same as the maximum R squared, but a little bit less. One person decided, hey, let's hack R squared and come up with something called adjust R square. And there is an adjustment factor. Let's talk about that. 1 minus R squared, ignoring the denominator, times total degrees of freedom over residual df. If we ignored all that df stuff, okay, this would be R squared, yes? 1 minus something. So we're adjusting 1 minus R squared by the total degrees of freedom. That's the number of data points minus 1 over the residual degrees of freedom. What we're doing is building in a penalty for a model that's too complex. If we have extra X variables that are not necessary, according to this criterion, SS error won't go down much by adding that unnecessary silly variable. If SS error doesn't go down much, R squared itself won't be changed much. But the degrees of freedom for residual will be adjusted because you're adding in an extra variable to your model degrees of freedom, 1 extra degrees of freedom for model, perhaps if it's a slope. And so residual degrees of freedom is going to be going down. R squared adjusted. Here's my over-the-top opinion designed to discourage you from ever using it again. Adjusted R squared's crap. Okay, so a lot of your faculty members will ask you, hey, what's your adjusted R square? I mean, you have to tell them if they ask you, especially if it's during your thesis defense. But you could say, we chose a different method for fitting our model. Adjusted R square is nice, but R squared at least has an interpretation. And adjusted R square for model selection is not optimal. Theoretically, there is no justification for adjusted R squared. Someone just said, yeah, we need a penalty term. Let's build it in a hack. Okay. How about theoretically optimal models? Mallows CP. If you ever see a number C with a lowercase p, it stands for Mallows CP. Colin Mallows, the only statistician I've ever spilled wine on at a party, invented this method. And he was very gracious when I spilled red wine all over him. But I will say, his method, great, but it requires you, theoretically, to be optimal. It requires you to be able to tell me your X variables in order. In other words, the first one to go in must be this one. And then you put them in line yourself. And if you do pre-order your X variables, Mallows CP can optimally choose your best model. If you cannot predict your, if you cannot put your variables in order of first one in, second one in, third one in, and then you're just picking a model size, we're going to recommend one of the following two methods. AIC for Akaiike Information Criterion, or BIC for Bayes Information Criterion. Sometimes BIC is called SBC for Schwartz Bayes Criterion. I'll just say, to summarize, AIC is optimal for choosing a model with unbiased parameter estimates. If your goal is coming up with a model where your parameter estimates, your slopes, if you will, are unbiased, AIC is the best way to go. Theoretically, and it's been around since the late 1970s, early 80s, we're happy with that. BIC, same idea, except for BIC is optimal for choosing the model that can predict the next Y value most precisely. Predicting the next value most precisely. PRESS, P-R-E-S-S, or sometimes it's called cross-validation or complete cross-validation. That's usually like BIC. The purpose being, let's use the data itself to determine which is the model we should use. AIC and BIC are theoretically justified. PRESS is more, or cross-validation is more of a, let's let the computer just run it through. And there is this unique situation where PRESS and BIC, again, are equivalent under certain theoretical conditions. So if you talk to someone and they're saying, oh, we did cross-validation for model selection, you'd say, good for you. You did something like BIC. If you want to use AIC instead, that's fine too. Another thing that you could use as a criterion, literally use a model where all of the terms are statistically proving themselves in the adjusted sums of squares. Let me say that one more time. Adjusted sums of squares says, controlling for all of the other x's, do I want this one also? And if the variable proves itself, you're saying, I should keep it. It's an x that does relate to y, and it helps me above and beyond all the other x's. Okay. So let's head towards which x's. You got, in this case, I got precipitation, humidity, January, July, or 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I counted it up. Without even the air pollution variables, I've got 12 variables that I could choose to use or not use. And let's think of 2 to the 12. That's 2, 4, 8, 16, 32, 64, 128, 256, 512, 10, 24, 20, 48, 40, 96. So there's 5,000 approximate models I could choose. I don't want to go and run every single one of those possible 4,096 models just to choose from one of those. I would like to have some sort of set of guidelines to utilize. So if there is an X variable, an explanatory variable you want to test, you need to include it in the model. Because if you don't have it in the model, you can't test a hypothesis about it. Similarly, if something in your discipline is theoretically, of course you need to include this because you need it. If theoretically you know there is an X out there, you've got to include that X. If third, if one of the X variables proves itself as definitely related to the response variable Y, probably you'll want to include it to control for the effects of that variable. Heck, even if including an X variable lowers the p-value for the variable you're wondering if it's related to the response. You have one X in mind to test for. Hey, by keeping this other X, do I clarify my picture? If it clarifies the picture, keep that X as well. Other X variables, don't keep any of them, would be the logic. So everything you need, because you need it to test, theoretically in your field, yeah, proves itself or clearly benefits you. There are still about 5,000 models here that I could run through, okay? And then I could ask these questions of all 5,000 models, okay? And I haven't even started down the path of interactions and transformations and polynomials or anything like that at all. So maybe what we should do is say, and this is getting harder these days, but we'll try it with the analogy that I like to utilize. If I am going to go visit my friend Sean, and he's recently moved to a new place in, I guess it's Henderson, Nevada, which is sort of southeast of Las Vegas. He used to live in Phoenix, and now he moved to Vegas. Then he moved to another place in Vegas because he built a home for some reason. And so if I wanted to go to his place, I'd say, Sean, what's your address? He sends me an address in the form of a text. I click on the button. Google Maps opens up, or Apple Maps, whichever it is, and it shows me initially not his street, not even Vegas. Well, Vegas is near the end at dot. Okay, it shows me roughly the whole journey from here all the way to there. Okay, it shows me I travel north on 101 to 46 east to 50 to 5 south to 58 through Tehachapi. I'm looking at the room here, and like none of you are nodding like, oh, you know this route. And then you go on 58 and you end up in Barstow, and then in Barstow somehow you get on 15 heading towards Vegas. Does that sound familiar to some of you at least? Okay, Jack's like, yeah, I go to Vegas regularly. I don't know if you're saying you go to Vegas, Jack, but that's probably the quickest route from here, okay? If you live far enough south, like Santa Maria, you might take a different route, 166, to Bakersfield, and then head that route. Or some people, if they're even further south in Santa Barbara, they go 101 to 126 in Santa Paula, then eventually you get on the Pearl Blossom Highway to Barstow, and you don't care about the routes. Okay, fine. The point is you get the big picture. the first glance at the map allows me to say, okay, I know about where I'm going. I know how to head out my door into Highway 101. I don't need a map to tell me that part. I don't need a map to tell me what to do until probably I get to approximately 15, 20 miles away from Vegas, because I know the rest of the route well enough. Not all of you would be in that position yourself. I mean, some of you have never been to Las Vegas, and so you might need a little bit more instruction. When I said things like the Pear Blossom Highway or 58 eastbound, some of you might have thought, I don't know this route. Maybe I should look at a map now. Some of you probably did look at a map. You probably typed in Henderson, Nevada, or Las Vegas and just looked at the Google map. And the reason for this long-winded analogy is I show you the big picture. The big picture is, get me in the ballpark. Tell me which are the X's I should use in my analysis. And then as I get closer to Vegas, I zoom into sort of the regional area and I say, okay, now I'm going to do some refining of my model. I know these are 4 X's that really do matter. These are 4 X's that really do matter. And maybe I'll later discover the first 2 need to be multiplied together in interaction. Okay, and then I may also discover after I add that interaction, maybe I'm going to need to go ahead and transform my y variable. Okay, so I'll go ahead and go back and fix that. And after I transform my y variable, I will be able to spot something. What I'll spot is, oh, there's another x that I had overlooked. Like in chapter 8, I overlooked an x. I put that, plotted the residuals against the x. I saw a trend. I put that x in. And then I'm going to go ahead and continue to refine or zoom in on now Henderson and then eventually Sean's neighborhood. And then I could follow the instructions. Okay, so this is the analogy. I don't know if it's a great analogy, but it's the one I like to use. I started it with MapQuest. Have any of you heard of MapQuest? So you're older students. Some of you have. Okay, fine. Our big picture map is going to be one of 4 things. Forward selection, backward elimination, probably neither of those, stepwise regression, or best subsets. I want to go through and describe forward selection, backwards elimination. Those 2 are necessary to understand what's called stepwise. And then I'll tell you what best subsets is. The way JMP implements all of these procedures looks really similar, okay? But you're going to end up using best subsets if your data set is small enough to handle it. If your data set is not small enough to handle best subsets, which literally does run every single model, but just reports on the ones that look good, you're probably going to be utilizing stepwise regression. I still see regularly in the literature as best subsets and stepwise regression, and stepwise is defined in terms of these other 2 procedures. Okay? So let's go through what forward selection is. Forward selection. I'm going to choose the variable that increases my R squared the most, gets me my highest model sums of squares. Or if you will, it turns out the lowest p-value. 2 different variants of the same thing. Depends on whether it's categorical or quantitative explanatory variable, but the 2 different approaches are the biggest bang for the buck in terms of R squared or sums of squares, or just p-value approach, choose the lowest p-value. The variable that I choose first is the one that does the best job explaining what's going on. That's it, first. Now, second step. Now that I've already got the first one in the model, which one will now be the one I should add next? Well, I looked through all of the possibilities for my first choice. I picked the one variable that was first, and now I've got all but one of them. So if I had 12 variables, I chose one of them, the lucky one. Now for each of the next models, I'm going to say, okay, go ahead. I've got 11 new possible x variables to incorporate. I'm going to try, of course, my first chosen variable plus each of those 11. I've got 11 new models. And I'm going to choose the model with the highest overall R squared, or if you will, highest sequential sums of squares, or perhaps the x variable that has the lowest p-value, having controlled for the first one, of course. Third variable in is the one that does the best job now that I'll have the first two in my model. Then the fourth one, and I've already got the first three, what's the best one to put in the fourth slot? I'm lining up the variables first, second, third, fourth, fifth in order, and they're always conditional. Always conditional. Now that is a lot of analyses that would need to be done. Okay, the reason that's a lot of analyses is in the first range, I've got to do 12, then 11 for the second step, then 10 for the third, then 9, 8, 7, etc. That's going to build up, and computationally, it can be a bit of a challenge. Someone said back in the 70s, oh my gosh, that's really hard to do with Fortran. So, hey, why don't we try this instead? It'll be quicker. Backwards elimination. Let's start with the model with all of the x's in it. All 12 are in there. And eliminate, kick someone out of the pool, eliminate the variable that does the least good for us, if you will. The lowest adjusted sums of squares or the lowest, or the highest p-value. Highest p-value, least proving itself worthwhile, or if you will, the lowest adjusted sums of squares. That's a variable that essentially is not getting me much. And then I with one regression, I could find the one worst variable, get rid of it. In the second step, I find my second worst variable, get rid of it. Third step, get rid of it. Fourth, get rid of it. And I, with both forward or backward, I would just continue until I'm happy, which could be defined as all the variables are significant. Okay, I'd continue until I'm happy with backwards elimination. There are other definitions for a stopping rule, but I just think happy is a vague way of phrasing that. But let's think through a hypothetical. If I was today with a data set exploring the relationship between several x variables and y. Y could be salary of someone. One of the x variables could be age of the person in the data set. Another x variable could be the number of years of education that person has. Another x variable could be the number of years work experience that individual has. And the context is maybe I want to see if males and females are paid the same salary for the same age and years work experience, etc. I have a variable on sex as well, okay, but I'm not considering sex just yet. If I was dealing with just age, okay, years work experience, and years work experience, and then years of education to predict salary. Think age, work experience, and education predicting salary. Forward selection picks age first. Age goes into the model first. The older someone is, the more they make on average. Age itself is the best single predictor of the three variables: age, work experience years, and education years. Okay, so there you go. Forward selection picks age first. And then it picks years work experience, and then finally education. Now, if we limit ourselves to certain sorts of jobs, the education and then the years work experience, they swap in order. Jobs which have sort of a requirement that you have at least a college degree, we'll see that those will end up swapping. Okay. If we had tried backwards elimination, again, age, years work experience, and then years of education, age is the first variable eliminated. So with forward selection, the first variable in, which does the best job, is also what backwards elimination says is the first variable to get rid of is the least helpful. Okay, at first you think, what the hell? That's not okay. Actually, it is, and it makes sense. Here's the way that it makes sense. It's not age that does it. More education does get you a higher salary on average, and more years work experience does get you a higher salary on average. And if you want a really good predictor of someone's age, take their years work experience plus their years of education, then add 5 to it for the number of years they were alive before they ended up in first grade or kindergarten. I mean, I have not met a whole lot of people who had long periods of time where they weren't in school or working, but are currently working. Among people that are currently employed, mostly you can predict their age very easily by saying how many years work experience do you have and how many years of school do you have. Take those two, add them up, add 5, and that's a good bet for their age. So it's not age that did it. Age is correlated with the other two. If you will, it's a multi-collinearity, like the poets and the legs, except for it's a bit more complex because it's across 3 variables. Backwards elimination and forward selection will choose often very different models. If you wanted to start at the top of Bishop's Peak and get down, you would say, okay, this is a big mistake, and please no one do this. If you take the step that will get you the furthest down on that next step, and then you keep the procedure going, take the next step that gets you for that next 3 feet forward, the greatest decrease in altitude, that's going to be a very different pathway than if you start at the bottom and go up, always going uphill at every step. The biggest step uphill from each current location will get you a very different path up the hill than the biggest downhill step starting at the top. Different paths. And I'm not saying one's right or wrong, just don't fall off the cliff like some people seem to do. Stepwise is like a combination of those two. It recognizes sometimes you have to go 2 steps forward and then 1 step back to make progress. Okay, so stepwise is the blending of forward selection, backwards elimination. Stepwise is usually something along these lines. Add a variable in, add another one in. Once you've added the 3rd one into your model, you say, hey, I've got this 3rd one now. Do I need the first 2? And if either of the first 2 are not helping me, get rid of the one that isn't helping. And then you add a 4th variable in. And then if any of the first few are unhelpful, you get rid of them. You add a new term one at a time. You're adding stepwise 1 new term at a time into your analysis. And then you're getting rid of a term if the new addition means you don't need the old terms. It's, if you will, exploring the model space. Now, when I say model space, that's sort of a challenging concept, but if you think sort of like a big old matrix. In a big old matrix, if you have for each of the 12 variables I'm considering them in a set of columns, you can either include them check or not include them no check. And depending on how many are checked in any given row, you're saying, okay, those are the ones that are in my model now. Forward selection is that you start with no checks, you add checks, and you keep adding checks. Backwards elimination, they're all checked, and then you remove some checks as you go down. Stepwise is you add a check, you keep adding checks, and then every time you add a check, you may end up taking one out if it's no longer helpful. And once we had built up the computational power to do all this, which was, well, let's just say somewhere between the 60s and 80s is when it was implemented on various different platforms, someone came along with this concept of best subsets. Let's just try them all. They said, we're already running a butt ton of regressions. We might as well run them all. And if the data set size is small enough, if k possible explanatory variables are in there, 2 to the k minus 1. If k is, 12 like we talked about, that's about 5,000 models. But if we had 20, anyone know 2 to the 20 off the top of their head or could calculate it real quick? It's big. Daniel's saying, yeah, it's big, but I don't know how big. This is curious how big. We're hoping you're unmuted because you have an answer. Okay, so what we've got from Chase is just over 1 million models. And if each model takes 1 second, a second isn't very long, but 1 full second could be the amount of time it takes to run an analysis if you have enough data points. 1 million seconds, that's like a long time, isn't it? Just humor me here and nod. Yeah, 1 million seconds takes a little while. So if you want to do best subsets, you're saying, I'm committed to trying every possible model. Minitab has built into it a little statement that says, yeah, are you really sure you want to use best subsets? If you say, please use best subsets, it says, are you really sure? This could take a long time. JMP is more recently written and doesn't have that warning built into it because of the faster chips these days. I'm still saying to myself, I've seen computers crash when you're trying best subsets. Let's say. So what I'm going to do is I'm going to just warn you first off, never use dummy variables, one for each data point in best subsets. That's a warning for the lab. I'll mention that next time before you go loose on the lab. So let me implement this, this algorithm, best subsets, with JMP here. And again, our goal is to try and see mortality as a function of, well, maybe these things, but ultimately those. And if I can spot any of these X variables as related to the response of mortality, I will want to incorporate them into my analysis. Ways to do that are going to be with, first off, maybe a scatter plot matrix, mortality through, mortality all the way through SO2. I'm going to just say, show me all those. And it appears over here. So I slide it this direction. And it's so big that I can't even see them all, but I can see most all of them. Okay, so mortality is along the left-hand column in the scatter plot matrix of all of the possibilities here. And I'm saying, well, this HC, NOx, and SO2, they're sort of hard to see a possible relationship. That looks like it's sort of positive. But I'm really starting with the question, is mortality related to any of these other X's? And right here, July temperature. That seems to be a relationship. I see a positive trend here. I see negative trend maybe with education. Maybe a positive trend with the non-white percentage. I don't know. We'll see. Graphically, I'd say definitely some of these, like right here, July temperature, does seem to be related to the response. Let's try the algorithmic approach. And again, we're going to try a whole ton of models all simultaneously. And we see where we get to under analyze. And this is under fit model. analyze fit model. Boom. I'm going to say mortality can be predicted based on, now I'm just going to choose everything except for the variables which I ultimately care about. This is not something you necessarily have to do. It's something I'm choosing to do now for the sake of what I know this data set is like, and it'll allow me to make another point a little bit later in the lecture more cleanly. So I'm just going to say mortality depends on all those things, but not yet the air pollution variables. And at this point in time, I need to identify the sort of model I'm going to be running. We usually use standard least squares, and we usually don't impact this or adjust this either. But under center polynomials, etc., it's just something you could do. A little red triangle, click on it, see what you have. Under personality, choose stepwise. I know I said that we're going to be doing best subsets, but stepwise is the way to get there. So under personality, stepwise. And by the way, this general linear model is different than that chapter 4 in our book implements. Do not use this generalized linear model until you've taken a different stat class, Stat 524. Okay? So under stepwise, we're going to use the procedure. Okay, so I'm just going to say stepwise is the procedure I'm using. Mortality could be predicted based on all of these things. I'm not including any possible interactions because that would make it even more complex than I want to deal with just yet. I click run. When I click run, I have a collection of output here, but I do spot, again, opportunities to either use forward selection. I could go forward. I could use backwards elimination, or I could use full-on proper stepwise. That mixed is what we call stepwise. Forward selection is in the category that's often termed as stepwise regression. Backwards, again, it's called stepwise for JMP's procedure. Stepwise / mixed is stepwise as it's traditionally defined. Stopping rule, minimum BIC. How about a p-value threshold? I could just click here and say stop when all of the p-values are below 0.05. Yeah, that could be my criterion. Or I could choose a different criterion, minimum BIC. That's the best model in one sense. Minimum AIC, the best model in a different sense. So if you wanted to run forward selection, backwards elimination, or stepwise, you could do it right now at this stage. I prefer to use best subsets, which is found over here. And our lab walks you through this, and we'll do this on Thursday. I want to try all possible models. Runs every possible model using a combination of the regression parameters specified. Click OK for every possible model. And how many model terms do I want to use? Do I want to go, up to models of 8 variables? No, I got 12. Let's go up to 12. Why the heck not? Number of best models to see. The maximum number of terms in a model is 12. Let's limit ourselves to the best 3 model for each model size. Now, sometimes you might want to choose the best 1 model if you're just poking around and want a quick fix. If you want to be thoughtful, you'd say, show me even 2 alternatives at any given stage. Okay, 2 alternatives. So I'm going to say 12 and 3, and you only have to worry about checking that box if you had interactions. I don't at this stage have interactions. I click OK. And a collection of output terms appear. Let's make it a little bit larger so we can see. The criteria you could use includes BIC. You could choose the lowest BIC. That's the best model. The lowest AIC, again, another good choice. But let's look over here across the different possible models. 3 best models up to a model with all 12 terms in it. So the 1, 2, 3 models of size 1 explanatory variable would be non-white percentage by itself, education by itself, precipitation by itself. I have the associated R squareds for each of those, the AIC for each of those, the BIC for each of these. And whether I use R squared here, RMSE, the lowest, RMSE best, AIC, the lowest AIC, or BIC, the lowest BIC, it's going to say non-white percentage by itself, as a model goes, is better than a model with education or a model with precipitation. The one variable model, I'm going to go with non-white percentage. So far, so good? Okay. If I were to say, what about models of size 2 variables? I'm going to go down to the next batch. So it looks like blue is what starts off a collection of criteria and a collection of models that you might want to consider. And blue is also the one that's deemed best for a model of its size. If I had non-white percentage, now we're saying education and non-white percentage are the two best possible models of size 2. Two variables in the model of size 2. January temperature, non-white percentage, over 65, non-white percentage, other alternatives. And one has an R squared of 56, a 54, and a 51. I guess barely a little bit better, okay? RMSE, lowest RMSE, AIC, best AIC is the minimum of them. Best BIC is the minimum of them. I would go with the model with education non-white percentage if I felt like I wanted to choose a model of size 2.
I have a quick question.
Yeah, please.
Does it matter the order of them? So like if it was non-white first, then education, or in this case, it's education, then non-white?
The order it's presented seems to be the order in the data set. Notice as you go down here towards the models, like the last model, precipitation, humidity, Jan, July, over 65, etc. This is the order of my X variables in my data set.
Okay.
And because that's the order in the data set, when they're presenting to me, various models, it's saying, well, we're going to keep that ordering in the way we're listing off the terms. So no, order doesn't matter here. And furthermore, if we had education and then non-white percentage or the other way around, the only place where that would really matter in a regression model with two X variables is if I did a sequential sums of squares, because I might want to say, controlling for education, does the non-white percentage matter? Or I might want to say it the other way around. But it's only when I really want to make one of those tests conditional, but the other one non-conditional, where the order is going to be an important feature. So I'm glad you asked that. Thank you. I should have been more clear about that earlier. Okay, so going down the list, I'm looking primarily to the blue ones, and I'm looking for maybe the lowest AIC. The lowest AIC model here, well, 6, notice that they go down, 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 and then they start to climb again. The reason AIC is climbing is it builds in a penalty for a model that's too rich, adding in explanatory variables that don't really help you a lot. We don't want to include those. So AIC has a penalty built into it. AIC basically is sort of like RMSE. It goes down, 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 down. But then as the model gets larger and larger with more variables, it's got a linear penalty term built into it. So although RMSE goes down when I go from a model with, while R squared goes down, the model complexity gets larger. And so we're going to choose the smallest AIC. In this case, the model, well, I'll just check it here. to remember. Precipitation, January, July, education density and non-white percentage, 609. Okay. If I had chosen the model with the lowest BIC, in this case, it happens to also be the same. They don't necessarily disagree, but they're using slightly different penalty terms. If there is a disagreement between AIC and BIC, BIC tends to choose a smaller model with fewer explanatory variables than the lowest AIC model would have. In this case, that's not what happens. One graph that's down sort of at the bottom, which is nice, is you can see our MSE for the model with one term, 2 terms, 3, we see exactly the variables listed off at each step along the way. And you can see it goes down, 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 RMSE does, then eventually it starts getting larger. And then on top of that, AIC has sort of a linear penalty term built into it or added to this, making this graph curve up even more. Same deal with BIC, except for it's not a linear penalty, it's a exponential penalty. Okay. I'm looking at this model here. The model with precipitation, January, July, education, density, and non-white percentage. This is the model I'd start with. I'm now almost to Vegas. I've crossed over state line. I've gotten to about where that first gas station is as you're heading into the Vegas area. You know, the gas station that's really expensive if you're heading out of town because they think, oh, well, it's just desert ahead of you. You're going to be willing to pay anything. Or the first gas station that you get to as you're heading into Las Vegas because you were an idiot and didn't get gas earlier in Barstow or somewhere. Yeah, we've all done that. You're willing to pay an extra 20 cents a gallon just because otherwise you're worried that you'll break down, 8 miles. So we're roughly there. We can then get a cleaner and clearer picture at this stage. So I want to go ahead and fit this exact model with those exact terms and then save the residuals and see, can I spot then some other issues that I'd want to be aware of. Okay, so under Analyze, Fit Model, I would fit the model where, again, we'll highlight these guys, mortality, depends on in order, and this is not a great order, but it is an order. It's just alphabetical, not alphabetical. It's left to right. July over. Oh, we skip over 65. Yeah, over 65. Apparently, it doesn't matter. Education, density, people per square mile, non-white percentage. There we go. And I'm sorry, it dropped in the wrong place. Does it matter? No. I'm going to run this. And like we were thinking we would see, you're going to do, according to what our model said here, we're going to have an R squared of about 71%. Here is that R squared. Hey, that looks pretty good. Residuals plotted against the Y hats. Yay, 71%. But, and shoot, all of these look pretty darn good, don't they? So with one quick analysis, we're really close. Every single one of these variables seems to definitely be related to the response Y. I want to keep them. Now let's go into the question. And I'm at this stage skipping the issue of interactions, quadratic relationships, and that sort of thing. I want to, because we have limited amount of time, I want to get to the, what would our conclusion be if we were to incorporate those air pollution variables? I want to sort of finish off that question because I know you're wondering. I'm looking around. The three of you aren't saying you're wondering. Okay, fine. I'm wondering if I were to include the air pollution models, or air pollution data, what would happen? And I'm going to actually choose to, at this stage, save my residuals. Again, these residuals are what we could not describe at all based on our x variables so far. We've got a collection of some x's. What could they not explain? And I'm going to look now if these residuals could be explained by things like the hydrocarbons or the nitrous oxide compounds or SO2. These three right there. And I'm going to choose, again, a scatter plot matrix, just because I can do all the plots simultaneously. The residual right there, along with my 1, 2, 3 air pollution variables simultaneously. Okay, right here. And that looks strangely something I could, oh, well, way too big. Sorry. Oh, well. Yeah, I see issues. The residual for mortality, can I predict it based on SO2 levels? Is there a positive trend here? Overall? Yeah. Is there a lack of equality of spread? Yeah. Now, we didn't include SO2 in our model, but certainly if I were to, it would have a positive slope, but there's an issue. What about hydrocarbons? That looks like a positive trend with a very steep slope, but there are these over here. So maybe there's a positive trend. Maybe hydrocarbons can predict the hydrocarbons and residuals, the residuals along the x-axis, residual mortality. Is there a relationship between residual mortality and NOx? Residual mortality on the x-axis, positive trend. Again, maybe some weird skewness going on. Same thing here. I'm spotting what looks like if I were to incorporate, okay, SO2, NOx, and hydrocarbons, these very unusual, very high values for some cities, but not for others. The bulk of the trend is not being well served by these two data points being incorporated into my analysis. Let's try our scatter plot just a little bit different. And looking at the time, I'm going to jump to a different scatter plot matrix. I'm going to say the residual. Does it relate to my re-expressed version of these air pollutant variables? The log of NOx, log of hydrocarbons, log of SO2. Okay, I saw earlier in the graph some dramatic skewness for each NOx, hydrocarbons, and SO2. More so for hydrocarbons than nitrous oxide than for sulfur dioxide. But that skewness made me think, what if I tried? What if I tried the residuals versus those? And for fun, I'm actually going to go ahead and put the residual in last, because I think that will be a little bit cleaner to read. The reason I think it will be cleaner to read is we're able to, across the bottom now, say the residual, could it be predicted by NO2 or NOx, the log of it? Positive trend. I mean, a weak trend, but a positive trend. What about hydrocarbons? A positive trend. A weak, but a positive trend. A log SO2? Maybe. Maybe that's sort of flat, but maybe it's positively trending. This one is less clear. If I were to put in these three variables in addition to my earlier variables, okay, maybe I'll benefit from including those additional x's. So I'm going to go ahead and try fit model one more time. And I'm going to show you, well, let's recall what we earlier had done. Those are our friends from before. Mortality, boom. I could put in precipitation down here, precipitation, and January, July, education, July, education, density, non-white percentage, and then the log version of each of those three x's. if I were to run that analysis, we'll see what happens. I earlier had a R squared of about 71%. I still am doing relatively well, I think. But let's see what we get for R squared. 77%. So about a 6-point bump in R squared. So we're happy about that. What do you feel about these air pollutant variables? Well, feel. What do you think about them? The model with precipitation, January, July, education, density, and non-white percentage suggested maybe some of these x's would matter. This is an adjusted sums of squares analysis. These effects test, if you will, they should be the exact same p-values, okay? Because we're dealing with only 1 degree of freedom terms here. These effects tests are not, okay, sequential. They're sequential but last. So in other words, nitrous oxide compounds, a p-value 0.0038, said, oh yeah, whatever else you had in the model, nitrous oxide compounds do help you explain what's going on. I would keep nitrous oxide compounds in my model. I got it. I've got to keep it. Hydrocarbons? Here's a question. If I put them in a different order, would hydrocarbons possibly float to the surface? Float to the surface, what does that even mean? Would it be proving itself worth keeping? I'm hoping for an answer from one of you all while I recall this model and rerun an analysis. What do you think? If I put them in a different order, would hydrocarbons or sulfur dioxide possibly be statistically significant?
If the effects test was adjusted sums of squares, probably not.
Okay, so what do you mean probably not? Definitely not. If nitrous oxide were last, the results should be the same because they're adjusted sums of squares. So it's not a probably, it's a certainly not. But the reason I did the reordering is I can now say, if I were to look at the sequential tests, and the reason I wanted to do this is for the final exam, one of the most common things for students to get not perfect if they choose the comprehensive form of the exam is sequential versus adjusted sums of squares. So what if I did sequential? Sequential test, okay, NOx, still that same p-value as before, but all of the other p-values are not necessarily the same. Certainly our effects tests and the sequential sums of squares p-values, they're all different excepting the last one. Hydrocarbons, still can't say it's necessary. Okay, what about sulfur dioxide? No. Is it hydrocarbons that did it? Controlling for these other X variables, we can say hydrocarbons seems to be related to lung-related deaths. Okay, and that's all lung disease or breathing-related deaths in 1972. This is just the age-adjusted mortality for each of these cities. And so we're just wondering, do we really have a relationship which would cause us to say nitrous oxide should be something that we would want to limit to keep people healthier? Yeah, seems so. Okay, that's about 5 minutes to go. Let me ask you, any questions for following up on any of this so far today? Takes a little bit of time to digest sometimes. Okay, well, what I'm going to be doing is shutting things down now. I'm going to stop the video and stop the share. And then what we're going to do, stop the recording and stop the share. And then we're going to, yes. And then we're going to call it a day. And next time we're going to start by talking about any questions you have. We'll then talk about the next step to take, and then we'll work on the lab, okay, that corresponds to week 9A. So the week 9A lab, not due, I'll adjust the due date to Tuesday of next week. So seems like a good place to wave goodbye.